All right, lecture 2 of our biochemistry unit. Let's jump right in. So we are here today to talk about water. It seems like such a simple thing. We take it for granted every day of our lives, but without it, there literally would be no life on Earth. Not just all the animals would die, but there wouldn't be an environment where life could actually be sustained. You guys probably have already heard things like water covers 75% of the earth, and it's one of the few substances on earth that's actually as a solid, a liquid, and a gas on earth at the same time. It's really an impressive molecule. I heard a quote once that says, if there's magic in this world, it can be found in water. And by the end of this lecture, I really hope you guys kind of come to understand how that could be true. So let's talk about its chemistry here. Its chemical symbol is H2O. You've probably heard that before. But why is it H2O? Well, that's because there is 2 hydrogen atoms and 1 oxygen atom. So here we have our oxygen atom and our hydrogen atoms. These atoms are going to share electrons. So you can see right here, these electrons are being shared by both. Their little lines are connecting to the oxygen and the hydrogen. We call that sharing a covalent bond. I'm not going to test you on that term, but just know that in order for these atoms of hydrogen and oxygen to come together, they have to share their electrons. Now, water has some very unique properties, and this is what allows it to really become that important molecule that we need for life. So, as a quick overview, we're going to talk about polarity, hydrogen bonding, cohesion, adhesion, capillary action, heat capacity, the fact that water is the universal solvent, and that it has a neutral pH. A lot of this is probably going to be new to you, but it's actually really simple, and once we put it into context of the real world, hopefully you'll be able to understand it. So the first one that really determines the rest of these, it's the reason why the rest of these properties can exist, is because water has polarity. So to make molecules, if you remember from our last lecture, atoms have to move their electrons around. They're either going to share them or transfer them over to each other. And we just said before that the hydrogen and the oxygen are sharing electrons between them. Now, sometimes atoms tend to be electron hogs. They like to hold on to the electrons a lot more than the other atoms in the compound. That's what's happening in water. Oxygen is what we call very electronegative. It likes to hold on to all of those electrons, and it becomes more negative because electrons, remember, have that negative charge. Now the hydrogen is kind of losing his electron a little bit. It's getting pulled further and further away from him. So he's becoming a little bit more positive. Remember that the center, the nucleus of the atom has protons and neutrons, and those protons are positive. The neutrons are neutral. They don't have a charge. So if I'm losing my little electron, I'm going to be left with just my positive charge in my nucleus. So this means the oxygen in water tends to become more negative, and the hydrogens in water tend to become more positive. So the definition of polarity is just that there's unequal sharing of electrons in a molecule to create positive and negative areas. All that's happening in polarity is we're sharing these electrons unequally. Oxygen is going to hog it a little bit more than the hydrogen will. So because of this property of polarity, water now has these positive and negative charges to it. And what happens when you have positive and negative charges in an area? Well, opposites attract. So we call this cohesion, when 2 polar water molecules stick to each other. The positive hydrogen will stick to the negative oxygen of a different water molecule. See, this is molecule number 1, and this is molecule number 2. They kind of look like Mickey Mouse, just all upside down or sideways Mickey Mouse here. So I have 2 Mickey Mouses, 2 water molecules that are connecting their positive and negative. Because remember, within my molecule here, I have covalent bonds where I'm sharing those electrons between the oxygen and the hydrogens. So my positive and negative polar areas will attract other water molecules. So it's the water molecules sticking to other water molecules because of polarity. Now, that force that pulls them together is called a hydrogen bond. These are weak connections between the opposite charges of 2 polar molecules, particularly with hydrogen. So these also can happen with hydrogen being attracted to nitrogen and other things like that. But for our case, in this class, we are just going to care about how it happens in water. So that little connection right here between the positive and the negative parts of 2 different molecules is the hydrogen bond. Now, this property of cohesion is important because it creates surface tension, where if you've ever set your hand on the top of water, it kind of feels like it's hard to break. If you've ever accidentally belly flopped in a pool, that's because there's surface tension. All of these water molecules are sticking together because of cohesion, and you didn't break those hydrogen bonds properly, so it hurt because it was like you were kind of hitting a wall there. Well, this surface tension is important because it lets many insects walk on water, and that's their habitat or their niche. But it's also important because it prevents a lot of evaporation loss. It's hard to break those hydrogen bonds, so the water won't evaporate as much. Now, the kind of buddy to cohesion is adhesion. It's still talking about polarity and hydrogen bonding, but it doesn't necessarily have to be the positive and negative areas of just water. There's other positive and negative things in the world as well. So adhesion is the tendency for water to stick to other surfaces with a charge through those hydrogen bonds. So if a water molecule gets close to something else that has a charge, like your skin, it's going to stick to your skin. That's why water doesn't just bounce off of you, like, say, if someone threw a dodgeball at you. It hits you and immediately bounces off. It doesn't stick to you, but water will. So this is how you get droplets forming on surfaces of things, like on the surfaces of leaves.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out.
So he's an astronaut on the International Space Station.
I dip this in a bag, but
and he's going to
bags
show
don't
us
hold water in space.
the properties
so instead,
of water
I filled a
without
water
gravity.
bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
So there you see cohesion. The water's forming a little droplet because it's all sticking to itself. So let's see what's going to happen with the washcloth.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth. And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
So at the end there, you could see that it was sticking to his hands because of adhesion, and it was sticking to itself in that tube around the washcloth because of cohesion. Now, these forces can combine to create a really cool phenomenon called capillary action. So a capillary is just a really, really small, thin tube. It's what we call the really tiny, thin blood vessels inside our body. So capillary action is the ability of water to climb through these very small tubes and seem like they're going against gravity. So if this is a little tiny dish full of water here, and we put different tubes inside of it, you can see how the water tends to climb upward. And the smaller the tube, the more the water is going to be able to climb. Because what's happening is, through adhesion, the water's clinging to the inside of the tube, and through cohesion, the water gets pulled up a little higher. And eventually, gravity is going to be too strong and it's going to break those hydrogen bonds. But what's happening in these kinds of tubes is that the hydrogen bonds are still a little bit stronger than that gravity that's acting on it. So it gets to climb higher, which is really cool. Now, in your life, you see this as paper towels. If you put a paper towel down on a spill, you don't even have to do anything. It'll just start to soak up the water off the table. Using a sponge, all of these things have tiny little pores in them, tiny little holes that will suck up the water through capillary action. You may have done an experiment like this as a kid where you took white flowers or lettuce or celery and you placed it in different colored waters. You used food coloring to change the color of the water, and you leave it there for a few days, and eventually you see that the plant starts turning whatever color the water was. And that's because it's soaking up that water from inside the cup through capillary action. And if it has a color, you can see it inside those veins of the plant. So this is how water can go from being inside the soil to being soaked up through the roots and the veins of the plant and go all the way to the top of the tall trees where it can be released through leaves. Pretty cool. Heat capacity is the next property of water that we're going to talk about. And heat capacity is the amount of heat needed to raise the temperature of a substance. So you would think, well, everything has the same. You just need to add a certain amount of heat and the temperature will go up. But actually, every substance has a different heat capacity. Some substances can absorb a lot more heat before they get higher in temperature. Some, it only takes a couple instants before their temperature can change. Water, we're very lucky, has a high heat capacity. This means it can absorb a lot of heat. It can take in a lot of that heat energy before it starts going up in temperature. And the reason why is because of all those hydrogen bonds. It takes a lot of energy to break those bonds. So you need more heat energy to break the bonds before you start seeing an increase in temperature. So you have large bodies of water like lakes and oceans that now, because of this, they don't change temperature very often. So you may have minor fluctuations of like a degree or two, but you're never going to see the water being the same temperature as the air, because at least here where we live, in the morning it can be freezing cold and then get to be 80 or 90 degrees by the middle of the day. Imagine if the water followed that trend. You'd have freezing water in the morning and really, really hot water that couldn't sustain life by the afternoon. So heat capacity allows all these big bodies of water to keep the same temperature so that animals and plants can live there and they don't end up dying because it's too hot or too cold. Water is also what we call the universal solvent. So its polarity allows it to attract the positive and negatives on other things as well. So certain compounds that are polar as well actually can get broken apart by how strong water is. And we call that dissolving. So in the picture here, we have a little hunk of salt. And salt is just sodium atoms combined with chlorine atoms. So that's why sometimes you may hear salt called NaCl or sodium chloride. Well, the water actually starts pulling all of these little parts away from each other, all these atoms away, and the water will surround the atoms and dissolve it. So when something dissolves other things, we call it a solvent. So water is a solvent because it dissolves polar substances. Now, water can dissolve so many different substances that we call it universal, meaning it covers many things. If you think of the whole universe, that's a large amount of space that includes all the material in the world. So universal means a large grouping. So it's the universal solvent. It can dissolve almost everything, but only polar substances. Now, this is important because what happens is chemicals inside our cells will dissolve in the water and allow chemical reactions to happen. And remember, I said in the last video that chemical reactions are essential to life. Without them, we wouldn't be able to move or breathe or even think. So the fact that water can break these materials apart and let them combine with other substances allows those chemical reactions to happen and we can live. And the last one we're going to talk about here is that water has a neutral pH. Now, pH is just a special measuring scale that we use to say if something's really acidic or really basic. So acid is just one side of this scale and base is the other side. Both of these compounds are very harmful to life. If you think of battery acid, you don't want to drink that because it'll actually kill you. It's so corrosive, we say, it'll eat away at other chemicals. So these are very harmful chemicals to life. Water, or the scale, I should say first, ranges from 0 to 14. Where 0 is really, really, really acidic and 14 is really, really, really basic. We don't want to be anywhere near any of those. Lemon juice is around a 2, which is really low. That's why you're told not to chew on lemons because they can end up eating away at the material on your teeth. And bleach is around 13.5. It's a very strong base. Water is 7. Which is right in the middle. It's actually not acid and it's not base. We call it neutral. So water has a neutral pH. It's neither acidic nor basic. And this gives water a very cool property that it can be used as a buffer. Now, a buffer is a material that can resist having its pH changed into something else. So With water, you can have other substances in it, but the water's not going to really want to turn acidic or basic. It's going to keep that mixture more neutral, which is great for life because we don't want to be adding things to our cells like our food particles to get energy and end up having our cells all of a sudden become too acidic or too basic. We don't want to have some molecules dissolve into a pond and turn it acidic so all the plants and animals die. So the fact that water is a buffer allows life to exist. So putting it all together, why is water so important to life? Well, capillary action is the special property that helps it climb up those thin tubes and allows water to be taken up by plants out of the soil. Hydrogen bonding, because of polarity, means that we have to break all those hydrogen bonds before we can increase the temperature. So it means water can take a lot more heat before it changes temperature. So our lakes and our oceans stay relatively stable in temperature. Now, water is the universal solvent. It dissolves many substances. So this allows us to have chemical reactions occur in our body, which allows us to live. Our bodies are mostly made of water. We're 60% water as adults. So we really benefit from this. And also, it's a buffer. It keeps the pH from going too crazy so that we don't end up damaging the important parts of our body or our cells. All right, see you guys later.